for any arbitrary normalized impedance point A on the Smith chart. If you rotate that point about the center, you would indeed find the normalized impedance on various points of a transmission line. If you look at the outer two rings on the Smith chart, you will see for the outermost it says wavelength towards generator, and for the second outer one it says wavelengths towards load. What this means is when you rotate in the clockwise direction, which is towards the generator, you are looking at the impedance at various points closer to the input of the line. And conversely, if you rotate in the counterclockwise direction, therefore toward load, you are then looking at the wave impedance at various points closer to the load. This means that, going back to our original setup where point A is a load impedance, we could rotate that point about the center to find the input impedance going into this transmission line. Now, let's say we have this transmission line with length 0.12 lambda. That's how much we need to rotate from the load toward the generator in order to find the input impedance. So to perform this rotation, it would be productive to first draw a circle that is centered about the center and intersects with point A. Now I'm using a graphical drawing tool, so I could just draw a circle, and if you use a paper Smith chart, you would have to draw it using a compass. Having drawn the circle, I want to know how much I need to rotate toward the generator to find the input impedance. I do that by first drawing a line from the center, intersecting with point A, and then going across outside of the Smith chart. And I'll take note of the value at the outer ring. So here it's 0.182, 184, 186, close enough to 188. I'll just say it's 188, 0.188. So bear in mind that this is in terms of lambda, but I didn't type lambda out. And the line is 0.12 lambda long. Therefore, I will add 0.12 to this, which is 0.308. So I keep looking on the outer ring and find 0.308. It's roughly here. And I'll draw a line that intersects with 0.308. And again, a little further out than the Smith chart. Having drawn this line, I can now put a point at the intersection between the green circle, which represents wave impedance in various points on the line, and this other line that represents the location of the input of the line. And if I read the normalized impedance of this location, the real part is roughly 1.1 and the imaginary part is roughly 2.1. The input impedance is 1.1 for the real part, minus, because it's at the bottom half, minus J 2.1. And by this rotation operation, we found the normalized input impedance to the transmission line, which we can multiply by the characteristic impedance to find the actual input impedance.